Hello, welcome to the video. In this lesson, we're going to be looking at section 10.2, where we're going to look at independent and dependent events. So we are going to determine if an event is independent or dependent and use the correct probability formulas to help us solve it. If we are looking at an independent event is when the occurrence of one event does not affect the occurrence of another event. A dependent event is when you have two events when one event one event does affect the occurrence of another event, and we'll take a look at different examples to help us determine which formula we are going to use. So first, here is the probability of when we are looking at an independent event. So if you have two events that are independent of each other, the probability of that both events occur will be as follows. So if you have two independent events, you're going to take the probability of the first event and multiply it by the probability of the second event if they are independent. So kind of similar to what we talked about in 10.1, here it says we are taking so a student is taking a quiz, randomly guessing the answer to 4 true or false questions. So we talked about that yesterday. Use the sample space to determine whether guessing question 1 correctly and guessing number 2 correctly are independent events. So they are independent events because getting question 1 right has nothing to do with getting question 2 right at all. So they are in fact independent events. So since they are independent events, we need to find the probability of getting question number 1 correct. Whoops. And it's going to be multiplied by the probability of getting number 2 correct. So hopefully you were able to look on page 539 in the text. There is the chart of the possible outcomes for getting the 4 questions either right or wrong. And we knew in the lesson prior, we know that there were 16 possible outcomes. So if you look at that page and if you were to count up all the times that you got question number 1 right, it looked like so for 0 right there was none, for 1 right there was 1, for 2 right looks like there'd be what 1, 2, 3, and then for 3 right 1, 2, 3, and then 4. So 3, 6, 7. It looks like there's 8. So for the first one, there's 8 out of 16 chance, which means you have 1/2 chance of getting number 1 correct from the 16 possible outcomes. If you looked at getting number 2 right, so anytime there was a C on question 2, there was also an 8 out of 16 chance, which ended up being 1/2. So the probability of you guessing on questions 1 and 2 is going to be 1/2 times by 1/2, which is 1/4, or about 25%. In this question here, it says a group of 4 students includes 1 boy and 3 girls. The teacher randomly selects one of the students to be the speaker and a different student to be the recorder. Use a sample space to determine whether randomly selecting a girl first and randomly selecting a girl second are independent events. So in this example, are they independent events? Yeah, because there's more than one girl in the group. Oh, there's at least more than 2 girls in the group, so there's 3. So there's the possibility of having more than one girl being the first and second choice. So to write this as like a sample set, I know this if you looked at it, in the sense of permutations where you have four students in the group and you're trying to figure out the order where 2 of them, where one's a speaker and one is the recorder, it comes out to a value of 12. And we'll look more about permutations later on in the chapter, but that is, again, that's how I saw it originally. But we can make a list of the potential outcomes. So you could say that, all right, so let's say since there are 3 girls in this, so just say like girl 1, girl 2, girl 3, and then you got the boy in the group. So first off, you could say that like girl 1 and girl 2 get chosen. You could also say that girl 1 and girl 3 get chosen. You could also say that girl 1 and the boy get chosen. Now that I've kind of used up all of girl 1 to be the first person, let's go to 2. So let's say it's girl 2 and girl 1. Then it's going to be girl 2 and girl 3. And then I got girl 2, and then the boy is chosen second. Now if we go everybody that starts with girl 3, so now I got girl 3, girl 1, girl 3, girl 2, girl 3, and we have the boy. Now I'll show you where each scenario where the boy gets chosen first. So now I got boy, girl 1, boy, girl 2, boy, and girl 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's where I was able to get the 12 from. So there's 12 possible outcomes. The question is to use a sample space to determine whether selecting a girl first and randomly selecting a girl second, what is the probability? So the probability of this, all right, so choosing a girl first, how many different times? So I have a girl first here, 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 and here. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 possible favorable outcomes, 9 out of 12. So 9 out of 12 chance of the first person being chosen is a girl. The second probability is for someone to be chosen. So it'd be So it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9. So again, there's still 9 out of 12. So if you were to multiply those together, so I'll just reduce it. So this is 9 twelfths turns into 3 fourths. 9 twelfths turns into 3 fourths. Multiplying together, this turns into um, be what? 9. All right, sorry. So uh, 3 fourths times 3 fourths gives you what, 9 over 16. So that would be now. Well, you have to look at the sample space and see, okay, how many have chosen uh, girls both first and second. So we have 1, 2, 3, 4, 5, 6. We have 6 out of 12. Now, is 6 out of 12 equal to 9 out of 12? It is not. So this means that this particular scenario is not an independent event. So this happens to be a dependent event. So in order for us to follow a dependent event, here is the formula. So the formula for a dependent event is right here. It is the probability of A multiplied by the probability of B knowing that A is true. So looking at this previous example here, they're saying that, okay, the probability of you choosing a girl first is 9 out of 12. Then you say you multiply by the second one, and then that one's going to be 6. There's 6 out of 9, which gives you a total of 1/2. And again, we'll show you some other ones that would also work out in that particular scenario as well. All right, so let's look at this one. It says, as part of a board game, you need to spin the spinner, which is divided into equal parts. They want you to find the probability that you get a 5 on the first spin and a number greater than 3 on the second spin. So the first thing you have to ask yourself is, are they independent or dependent events? So is there anything that would impede the second event if the first event occurred? And the answer is no. So this is an independent event. So we're going to be using the formula that we got in the first on the second page, which is the probability of A times it by the probability of B. So probability of A is, what is the probability of us getting a 5? Well, since there's one slot that's a 5 and there's 8 slots total, it's 1 out of 8. The probability for part B is something getting greater than 3. So getting a 4, a 5, a 6, a 7, or an 8. So 4, 5, 6, 7, or 8. So there's 1, 2, 3, 4, 5. So it's a 5 out of 8 chance of getting that. So the probability of you getting a 5 and a number greater than 3 is going to be 1/8 times it by 5/8, which is 5 over 64, which is about 7.8%. So here it says a bag contains 20 $1 bills and 5 $100 bills. You randomly draw a bill from the bag, set it aside, and then randomly draw another bill from the bag. They want you to find the probability that both events A and B will occur. So The first event is the first bill is a $100. So so there's 20 and then 5, so there's 25 bills total. There are 5 $100 bills, so you have a 5 and 25 chance of getting that. So 5 divided by 25, that is 1/5. So you have a 1/5 chance of getting that. Part B, it says the second bill is $100. So since you set it aside, that means that this particular one is a dependent event. Now, the dependent event means that looking at the probability of the second one is you already have to assume the first one was correct. So you have to assume that the first one you drew was $100. So how many bills are in the bag? Well, once one was taken out, there are 24 now. And since one $100 bill was already taken out of the bag, there's not 5, but there are 4 remaining. So you have a 4 in 24 chance of the second one getting a the second one being a $100 bill, and that is a 1/6 chance. So the the probability that both events will occur is going to be 1/5, which is the probability of A, times it by 1/6, which is the probability of B knowing that the first one did work. So 1/5 times 1/6 is 1/30th, or about 3.3%. Here it says you randomly select 3 cards from a standard deck of 52 playing cards. What is the probability that all 3 cards are hearts when A, you replace each card before selecting the next card, and B, you do not replace each card before selecting the next card? So essentially, one is an independent event and the other one is a dependent event. So looking at part A, it says you replace it. When you replace the card back into the deck and then select it again and again, that is the independent event. So essentially, you are getting for part A, it's just essentially the probability of A times like the probability times by the probability of B, the second one times by the probability of C. So the probability of you getting a heart, there are, of 52 of them, there are 13 cards that have hearts on them. So you have a 3 out of 52 chance the first time. Because you replace it, you have a 3 in 52 chance the second time, or 13 in 52, and a 13 in 52 chance for the third time because you replace it. So you're just going to multiply all of these together. When you do that, you get 2,197 on the top. You get 140,608 on the bottom. It gets reduced to 1 out of 64, which is about 1.56%. Now for part B is a dependent event. The reason why it's a dependent event because you do not replace each card before selecting the next one. So you have one less card in the deck. So for part B, what it's going to be is you got the probability of A times it by the probability of B knowing that A occurred, and then the third one's going to be the probability of C knowing that A and B occurred. So the first one's like just like the top one, you got a 13 out of 52 chance of getting one. Then you're going to multiply, you're going to select another card. Now, there's one less heart because you selected one in the first one, so there's 12, and there's one less card total, so that's 51. And then, looking at the third one, you have one less heart, again, because the other 2 were selected, so you have 11 over, there's one less card in the deck, so now there's 50. So this is what it happens when you don't replace it back into the deck. So now when you multiply it across, the top is going to be 1,716, and on the bottom, it's going to be 132,600. This gets reduced to 11 over 850, which gets you a rough percentage of 1.29%. So you have a better chance of getting 3 hearts um, cards in a row if you replace it rather than not replacing it. It's a smaller, they're both small chances, but your chances are greater in the independent event. Here it says a quality control inspector checks for defective parts. The table shows the results of the inspector's work. They want you to A, find the probability that a defect part passes, and B, the probability that a non-defective part fails. So for part A, they want you to find the probability that a defective part passes. So we got our defective parts. 3 of them, 3 times they pass, 36 times they fail. So the probability of this happening is 3 out of 39 times because there are 39 total times that it defected and 3 times it passed. So if you reduce that, it comes to what, 1 over 13, which gets you about 7.7% probability. For part B, they want you, says the probability that a non-defective part fails. So non-defective part, how many times they fail? It was 11, and the total number is going to be 450 plus 11, which is 461, and that is a rough percentage, about 2.4%. Finally, they're asking here, it says, at a school, 60% of students buy a school lunch. Only 10% of students buy lunch and dessert. They want to know what is the probability that a student who buys lunch also buys dessert. So the way they word this problem is interesting because they say like they want to know the probability of a student who buys lunch will also buy dessert. And they also say here that 10% of students who do buy lunch and dessert. So here is how you kind of go about solving this one. So on the top, what you're going to do is you're going to attach uh, the probability that a student who buys lunch gets dessert. In this case is 10%, but you're going to convert that to a decimal. So 10% as a decimal is 0.1. Divided by, you're only looking at the students who buy school lunch. And in that case, that's 60% of the students. And as a decimal, that is 0.6. So 0.1 divided by 0.6, that is a probability of 1 over 6. So about 16.7% of students who buy lunch would buy dessert. And that is being able to look at independent and dependent events. Hope this helps. Till next time.